Well, hello and welcome to the ANiMAL, the Artificial Neural Network and Machine Learning. This is a practical realization of neural networks as conceived in Excel. It uses nothing more than the basic Excel instruction set. And for a free version of the spreadsheet, go to www.wellmonitoringservice.co.uk. This is supposed to be a user manual for the freely available Excel spreadsheet. But we need to do more than that. We need to add a little bit of detail of how it works, why we call it the animal jigsaw, for example. At the moment, we've got 2 hidden layers and 5 neurons in each layer, so we've got 10 neurons in each. If you find anything wrong with it, please let me know. If you find any improvements, please let me know too. We've tried to look at the brain and nick ideas from it, and we have done so. Not just the neurons, but other things as well. But that's in a separate paper. Right, first of all, let's get back onto the animal. This is the main equation. It's 50, 60 years old, but nothing else has come out apart from the neurons in the brain, which is a bit of a shame. But anyway, so we have inputs to this particular neural network. We have weights, they call weights, and then they are multiplied together and summed. And then a bias is input as well. And then we have this activation function. So the output is an activation of X. So we have all this, the affine function, activation function of X. Now the neurons normally are described in little circles, and these are the weights, weight 1, weight 2, weight 3, etc. And we have 1, 2, 3, 4 neurons. We have an input and an output, and the biases. So rather than put everything in the neuron here into I wouldn't say a big equation, but it's one equation of this input times this weight plus this input times that weight, and then you take bias into consideration, and then you take the sigma, or you take an activation function. So rather than do all that, I have found if we spread it out a bit, it's much easier to fault find. For example, we have up to 5 inputs in this particular neuron. So this is the equivalent to a neuron. We have an input, we have weights, and then we have the sigmoid of that times that plus that times that plus that times that plus that. Yeah, and that all comes out to that. Then we add in the bias, or rather subtract the bias, and take the sigmoid of it. And then we multiply it by the shrinkage coefficient, shrinkage and expansion coefficient. This is relatively new. We've found now that neurons die or are repurposed if they are not used. And so you can have a shrinkage, a synaptic shrinkage. But also we have looked at, so that is basically the neuron. But basically we've also found that there can be an expansion coefficient, because this is a biological neuron, the nucleus, the dendrites, the axon, and that can go into another neuron. Fine, but it just doesn't have one input, it can have many inputs. Now why is this? We've only got one output. Well, we've got one output, but it can be fed into the same neuron. So rather than just have one as a factor and use synaptic shrinkage or naught, we can have a multiplication factor and see how that works. Now the sigmoid logistics it works quite well. However, and that's the equation. What a simple equation. Just write that in and it all seems to work. The only trouble is that we've got a vanishing gradient problem, and this can result in the network refusing to learn further or being too slow to reach an accurate prediction. I certainly feel that in our animal, but we can just easily get over it by resetting the weights and resetting the bias, or doing something to overcome this. This is not, the animal is not a solution generator. It is a suggestion maker. It suggests outputs and we can approve them or not. So now we've got two neurons, okay, in hidden layer 1, hidden layer 2. We haven't got an output yet, but two neurons. And this is the input. Here we call it the up to 5 inputs. Let's say maximum temperature 3 volts 1. We have to have that prepared. We can't have, as I said, we can't have 1,000 in here. It will just blow it up. So in this case we have to divide by 1,000 and it gets it into a reasonable range, and then we can multiply it by the weights and take the sigmoid, add the bias, and then do the symptotic output, and that output goes to that input. It hasn't got any other inputs because they'll be down here and they haven't got any here, and then we get the output. So that is the basic, and then you can start to see what we call a jigsaw, because we just take this and we copy and paste. We go whatever we want. So it's very easy. Oh, there we have it. So this is a 4 neuron. Right. Once we have an output, these weights are all random numbers. It's amazing it actually works. They're all random numbers. And so we need some sort of feedback mechanism to adjust these weights and these biases, and these weights and these biases, so that it can get better, it can improve. And we can do that through the output coming back into and affecting these weights and biases. See? So we've got 10 neurons here, and then we've got another 10, and another 10, and another 10, and we can go all the way down. And it's very easy, as I said, it's very easy to fault find. Anyway, we were coming into the error. Now the error is here, and this is, yeah, there we are. So we have the factored answers, what we know the answers to be, and the animal's answers. That is what gives us the error, and we solve in Excel, we solve to minimize that error. This neural network uses 10 neurons, up to 10 neurons. It is preferable not to use too many, otherwise you get overfitting. Right, let's move straight on. Now this is the flow menu, as it's called. We start with entering data up here. We then train the animal. We then enter live data, the patterns that we want it to analyze, and then we can look at the recommendations. And then we can look at animal analysis, all the 10 cells, the 10 snapshots of animal, and we look at the synaptic shrinkage and expansion review. So very quickly, let's go into them one by one. So if we go into training data, this is relatively straightforward. So we have, the convention is any white cells are user changeable. Anything that is grey or coloured has got equations behind it and should not really be changed. Input. Here we have the 10 snapshots of the 10 neural network. So we have 10 neurons, 10 times each, so that's 100 neurons. Each snapshot is trying to recognize a pattern of data of up to 5 parameters. We can set the parameters to whatever we want. We can set the preparation factor. For example, here we're dividing it by 1,000. Here's 10 and here is 1. So we set an output, an answer, 1, 2 or 3. 1 means it won't work. 2 means it might work, needs review, and 3 means it should work. So those data patterns, we are trying to train this network to recognize good patterns and bad patterns. Doesn't matter what the data is. Actually, it's to do with well monitoring, water well monitoring in Tanzania, and we're trying to predict when the wells break, so we can send a team out to fix them before they break, and therefore supply water continually. Right, so let's go back to the flow menu. The flow menu is here. Flow menu is a concept that came from the brain as well, actually, as a synaptic expansion, and is the major oblongata. But anyway, now let's go into training the animal. Right, if we go into training the animal, we click in here, we can see that we have a number of boxes. We can use some preset weights and a bias set, or we can reset the bias individually or reset the weights individually, and we can run the solver. Once we run the solver, that will give us the animal's error or its confidence in the answers. When we run these and run the solver, once we get a nice answer, then we can record it as a saved set. Let's run the solver. If we run the solver, and it's improved it dramatically. If we run it again, that's improved it dramatically as well. Go and have a look at the next step, which is enter live data. Right, we've trained the animal, and now we're going to enter live data. Now this is quite straightforward. All we have to do is to enter. So we're putting in 4.9 volts. Now if you remember, 4.9 volts was going to be a fail, so we're expecting an output of 1. So that's where we put in the live data. Right, now let's go into looking at the animal's recommendations. We've entered the training data, we've trained the animal, and we've entered live data, and the animal's recommendations are 11.9, which is ridiculous, because it's got to be 1, 2 or 3. So if we get is recognizing a pattern, and it's going to be 1 for fail, 2 for check, and 3 for pass. Well, this is completely wrong, and its recommendations are also saying it's red. So its own confidence in its result is pretty poor. So it knows it's wrong, but it doesn't know quite how to put it right yet. But we can do that in a minute. So what do we do about it? Well, that's when we go back into training the animal. I don't know whether we can run the solver again. Oh, there we are. We run it, and it gets better. And go up to the flow menu again and say, right, what's the recommendation? The recommendation is, look at that, 0.096. So it's saying it's very close to a 1, which is a fail. Now it's strange, but it's a fail, and it's fairly confident. It's given us a green light. The confidence in this result is good, and that's what it does. So we've given it some training data, we've given it some live data, we've trained it, we've got an output. As soon as we change something in the network, we really should run this again, because if we don't, we will tend to get incorrect results. That summarizes the artificial neural network in machine learning, and it's all in Excel, which is amazing what it can do. All right, thanks very much for watching. Cheers then. Bye bye.